Okay, so now we are ready to start a systematic study of conformal field theory. So, at least initially, let me tell you what we're going to try to do. So, we'd like to start off by specifying exactly what we mean by the conformal group. Once we've understood what the conformal group is, so the generators for the conformal group, how do I generate these transformations? I'll then want to know how is conformal symmetry realized on the fields of our quantum field theory. And this basically amounts to building representations for the conformal group. Once we've done this, we can start to cash in on this progress, and we can use these insights of how the conformal symmetry acts to start to constrain observables. And the basic observable that we are interested in is correlation functions. Once we've done this, we would be able to calculate, for example, critical exponents and the dimensions of some operators. So this is going to keep us busy for a little while, but I just wanted to let you know sort of where we're going. So we're going to start off, and the first question that we would like to answer is, what is the conformal, uh, what is the conformal group? Conformal group. And we're going to start off by answering a slightly simpler, more familiar question, but the methods will then immediately generalize to the conformal group. So we're going to start off to start. So first, let's just ask, what is the Poincare group? Now, I'm sure that you all know what the Poincare group is. So what is the Poincare group? And you know that the Poincare group is a group of 4 translations and 6 Lorentz transformations, 3 rotations and 3 boosts. But the way to actually specify the Poincare group is we can say it is the set of coordinate transformations that leave the Minkowski metric invariant. Now, the reason why it's nice to say it like this is that this actually gives us a condition that we can turn into an equation. So let's imagine a coordinate transformation. So we take x mu and we transform it to get some x tilde mu. And then this condition that it leaves the Minkowski metric invariant, we can encode this in an equation. So let's start off with eta mu nu dx tilde mu dx tilde nu. So what is this equal to? Well, under this change of coordinates, this becomes eta mu nu dx tilde mu d uh, um, dx alpha dx tilde nu dx beta dx alpha dx beta. We have done nothing here. We're just using the normal rules that you know for partial derivatives. So for example, if you had a function u, which is a function of x and y, and you want to calculate what is the variation of u du, well, this will be equal to du dx dx plus du dy dy. Okay, calculus linearizes everything. To get the change in u, you calculate the change due to x, you calculate the change due to y, and then you just add the two of them up. And exactly the same equation, it's exactly the same equation, just using the summation convention, we can say that dx tilde mu is equal to dx tilde mu. Ah, this is getting a little bit busy. Let me see if I can do something about that. Good. Uh, so let's just, so it's exactly the same equation. There's no difference. We can say dx tilde mu is equal to, and now we work out the changes due to a change in dx alpha, and then we just add them all up. The summation convention adds all of that up. Okay, so we didn't do anything there. And we know that if we want this to be invariant, this must be equal to eta alpha beta dx alpha dx beta. Now, this is nice because we immediately get an equation. You see, these dx alphas and dx betas, I can choose them as I want. So if I want this line over here to be equal to this line over here, I really have to require that eta mu nu dx tilde mu dx alpha dx tilde mu dx beta. So that's the coefficient of dx alpha dx beta, and this is equal to eta alpha beta. Okay, so the nice thing is that this equation over here, we are going to see this determines the Poincare group. So from this equation, we'll learn there are 4 translations, 3 rotations, and 3 boosts. So 4 translations and 6 Lorentz transformations. So nice. We specified our group by an equation. When we want to analyze this equation, the logic is always the same. So remember this is a good idea. We're always going to study an infinitesimal transformation. So concretely here, how do we study an infinitesimal transformation? Well, we say, let's imagine that x tilde mu is equal to x mu plus zeta mu. So that's certainly a coordinate change. But the other thing that we're going to say is that this zeta mu, this last term over here, this is what is infinitesimal. And because it's infinitesimal, if I ever get a zeta times a zeta, I can just drop it. So that's how things simplify. I don't have to bother about any nonlinear terms in the zeta mu. Okay, good. Now, what we're going to do is we're going to take x tilde mu is equal to x mu plus zeta mu, and we're going to plug it into that equation in the black box. And that's how our equation in the black box determines our group of transformations. So what must we calculate? We must calculate dx tilde mu, dx alpha. This is one of the things appearing inside the black box. So we're just going to take d by dx alpha and let this act on x mu plus zeta mu. Just plug that in. And this is, we usually write this as d alpha x mu plus d alpha zeta mu. So no big deal here, just a change in notation. And d alpha is always taken to be a derivative with respect to x alpha. And then what is this equal to? Well, the first term is 1 if mu is equal to alpha and 0 otherwise, plus d alpha zeta mu. Great. Okay, we'll continue in a moment.